Alright, so let's get started. Good evening and welcome to Advanced Electrical Networks. This is lecture 26. So, in the last class, we were talking about why time varying systems are important and why it indeed makes a lot of sense to study them. And it's only surprising that we never get to study these things for some strange reason or the other. So, let's get, so today we will begin in right earnest. And it's always much easier to understand things when you try to relate it to something that you already know, and the closest material that you know is stuff about linear time invariant systems. So, we would like to, as we keep going along, we like to keep drawing parallels between time varying systems and time invariant ones, so that you can use what you have learned to kind of use that as a baseline and see where you extend the concepts, and hopefully this will build intuition. So, quick refresher about time invariant systems. Well, so you have an input x of t, and a time invariant system is characterized by an impulse response h of t, and the output of the system therefore is gotten using the very familiar convolution integral, which I will simply derive from scratch, just so that we can do the same thing when we go to a time varying system. So, this is x of t, and let us say you are interested in finding the output voltage, output quantity at a certain time t, and the signal tau before, this is the time of observation, t is the time of observation, and this thin sliver here that occurs, that's occurring at a time tau before the time of observation, this time therefore is t minus tau, correct. This can be approximated by a Dirac impulse of with strength x of t minus tau times, this is delta tau, correct, and so that is the strength of and that this impulse occurs at a time t minus tau. So, basically this is the strength of the impulse, and this impulse occurs at t minus tau. So, so that is basically the right. The response to this impulse is, the response to this impulse at time t is simply given by h of, I get t, I get tau, I get t minus tau. It is simply you apply the impulse at t minus tau, you are observing it at t. So, the response to this impulse is basically x of t minus tau times h of tau d tau, correct, and you integrate this, I mean to find the total response at time t, you kind of keep sliding that tau all the way from zero. I mean you start here, I mean you assume that h of t is causal, I mean you assume that the impulse response is causal. So, the system is not responding to inputs that can potentially occur in future. So, you run you integrate this from tau equal to 0 to, when tau equal to 0 you are basically looking here, and then x of t of course can extend all the way from minus infinity. It does not there is no reason why x of t must start from 0, though in this picture it does, right. I mean we could still be responding to an input applied in 3000 BC, I mean, right? I mean, nothing prevents that from happening, right? So, this goes from tau equal to 0 to infinity, correct? So, this is the very familiar convolution integral, I mean, there is really nothing much to discuss. Now, let us see what happens in, so this is convolution. Linear time invariant system. Now, a linear time varying system or LTV, right? The only difference between a linear time invariant system and a time varying system is that, well, if you get x of t, let us say you got y of t, and if you put, it is still linear. So, alpha x of x1 of t plus beta times x2 of t will yield alpha times y1 of t plus beta times y2 of t, and so superposition is still valid, right. However, x1 of t minus t naught will not yield not necessarily yield y1 of t minus t naught. Okay, so this is not time invariant. All right. So, in other words, if you apply an impulse, so let us say again, we are faced with trying to figure out what the output of a linear time varying system is to an input, right. Again, we resort to the notion of the impulse response, right, and just like how we worked with a linear time invariant system, what did we do there? We split up this input x into a whole bunch of impulses, and then we know the response to each impulse, and we added up the response to each one of those thin slivers, and then that is how you get the convolution integral, correct. Now, we are going to do the same thing, except that, so let us say we break this up into impulses. So, this is a sliver, this is yet another sliver, each of which is approximated by an impulse, right. When we had a linear time invariant system, the response only depended on the time difference between the point at which the system is excited with the impulse and when you are observing the output, right. It did not depend on the fact that, I mean, you launched it particularly at t minus tau and you are observing it at t. If you pushed t minus tau and t both to the right, for instance, by the same amount, the response would still be the same, correct. That is what time invariance means, right. A time varying system is where it depends both on the actual time of observation as well as the actual time at which the impulse is launched, right. In other words, the impulse response is of the form h of t comma tau, where t is the time of observation and tau is the time before t at which the impulse is launched. Okay. In other words, h of t comma tau basically means that the impulse is launched at what time? At t minus tau. Okay. I mean, this is just a matter of notation. There is nothing, you know, holy about this. It's also quite common to have a notation where where the tau denotes the time at which the impulse is launched, right? You excite at tau, you observe at t. That's another alternative notation. I just chose to use h of t comma tau as where when I say h of t comma tau, it is the response at time t due to an impulse applied tau earlier, right? So, the impulse is applied at t minus tau. Does it make sense? All right. And so, an LTI system is a special case of an LTV system where h of t comma tau equals, it is independent of t, it is only a function of tau, correct? All right. So, next thing, again I will keep back and forthing between a time invariant system and a time varying system, so that we see the parallels. Now, as you all know, the complex exponential is a very important signal when you work with linear systems, right? And that is because it is an eigenfunction of a linear system. Let us see, let us refresh our memories as to how a linear time invariant system reacts to a complex exponential e to the j omega, e to the j 2 pi f t. So, let us say x of t is e to the j 2 pi f t, and then it starts at minus infinity and then keeps coming all the way. So, y of t therefore is, you plop x of t into the convolution integral and you basically get 0 to infinity e to the j 2 pi f t minus tau h of tau d tau, which is e to the j 2 pi f t times integral e to the j 2 pi f, sorry, let me write this as h of tau e to the minus j 2 pi f tau, correct? And this is only when you perform this integral, of course, the tau is going away. So, this is going to be a function of f. So, basically this is nothing but h of j 2 pi f, right? And what is the name of this? So, a couple of things to note. If you put in a complex exponential, right, the output is also, in other words, if you put in a sinusoid, the output is also a sinusoid, except that this sinusoid is gained up by a complex number. The gain, so in other words, you can think of h of j 2 pi f, or the frequency response, as the response to e to the j 2 pi f t divided by y of t is the response to e to the j 2 pi f t. So, if you want to interpret h of j 2 pi f, how do you interpret this in English? Is the ratio of the response to e to the j 2 pi f by e to the j 2 pi f. Right, you knew this already. So, all right. So, in other words, this h of j 2 pi f, if you want to think about it, it is simply the gain experienced by a sinusoid when it passes through the LTI system, and of course, this gain is a complex number, meaning that it will, in reality, what it means is that not only do you see a change in the magnitude, you also see a phase shift. Correct? Now, the system is time invariant, and what does time invariance mean? I mean, time invariance means that nothing changes as far as the system is concerned, because if you excite the system now, or if you excite the system a day later, you get exactly the same response. Since the system is not changing with time, it seems reasonable that the gain experienced by the sinusoid also does not change with time. Correct? Alright, now let us do the same thing. Let us see how our time varying system fares with the sinusoidal input. So, we need to figure out the convolution integral first. So, so the response at time t due to this impulse here is what? Is nothing but h of t comma tau d tau x of t minus tau, correct? And then what do we run the integral over? Tau is 0 to infinity. All right. Okay. So, this is the convolution integral for an LTV system, and as you can see, sanity check, if h of t comma tau is the same as h of tau, which is what it would be if the system is time invariant, then you get back the familiar convolution integral that you are used to from your study of time invariant systems. Is this clear, people? All right. Now, as usual, it's a linear system, so we'd be interested in figuring out what happens to the system when you excite it with a complex exponential. And what is so special about a complex exponential, by the way? I mean, why are we interested in complex exponentials? Pardon? Yeah, so what does that mean in English? So what? So what? Yeah. So the motivation to use sinusoidal signals is that any signal can be decomposed into a sum of sinusoids via the Fourier transform. Okay. So if you figure out how the system responds to one sinusoid, or to a sinusoid with a frequency f, you can figure out how it responds to an arbitrary input. So x of t is e to the j 2 pi f t. So, y of t is integral e to the j 2 pi f t minus tau h of t comma tau d tau, right, and this is e to the j 2 pi f t h t comma tau e to the j 2 pi f tau, correct. And again this is the same sanity check. If h t comma tau was independent of t, then you get the familiar Fourier transform that of the impulse response, which is the frequency response that we all know. Now, what comment can we make about this this guy here? We integrate with respect to tau. So, this after integration, what do you get? You will get a function which is this will be both a function of j 2 pi f as well as, does it make sense? Alright. So, what do we see now? When you excite a linear time varying system with a complex exponential, the output is that complex exponential multiplied by a gain, right. The gain, as you can see here, depends not only on the frequency, but also on time, right. Now, does this seem reasonable? Or does it seem unreasonable? Okay, and this seems reasonable because, the system's properties are varying with time. So, it seems reasonable that you excite it with the sinusoid, and therefore, the gain the sinusoid experiences as it goes through the system will also vary with time, right. And as before, how did we interpret h of j 2 pi f in the time invariant case? We interpreted h of j 2 pi f in the time invariant case as the ratio of the response to e to the j 2 pi f divided by e to the j 2 pi f, and that is the same thing here. So, h of j 2 pi f comma t is simply response to e to the j 2 pi f t divided by e to the j 2 pi, like in the right. And what comment can we make about h of minus j 2 pi f comma t? In other words, if we excited it with if f was made minus f, what would we get at the output? Okay, so we got, when we put in e to the j 2 pi f t, this is what we got. If we put in e to the minus j 2 pi f t, what would we get? You would get e to the minus j 2 pi f t times, all that you need to do is replace f with minus f, right. And so, that becomes 0 to infinity h of t comma tau e to the j 2 pi f tau, and this therefore is, what is this? H of minus j 2 pi f comma t. And how does this relate to h of plus j 2 pi f comma t? Is the complex quantity, right. So, h of minus j 2 pi f comma t equals h star of j 2 pi f comma t. And the assumption here is of course that h of t comma tau is real, right. Okay, does this sound familiar, or is there, I mean, is there something, sanity check? Yeah, I mean, well, if the system is time invariant, then the gain won't depend on t, and we know that, I mean, there must be odd symmetry about, I mean, the complex conjugate, when you change f to minus f, you must get a frequency response which is the complex conjugate of that. So, magnitude and phase will be, even and odd functions of frequency. Does it make sense?